Well, hello friends. Welcome back to the program. Today we're going to continue working on the JavaScript JIT compiler, and we're going to circle back to the first loop program that we created just to prototype the JIT in the first place. And it's a simple function that just loops 100 million times, does nothing, and returns. And this is a very simple thing, but it still runs pretty slowly in our JIT right now. If we time it, we see that it takes about 1.14 seconds, and we're going to profile it actually so that we understand exactly why it's taken so long. But I guess I can run that while I'm talking. So what the profile is going to tell us is that we're spending most of our time in these C++ native code helpers rather than in the generated assembly code, because over the last couple of videos, as we've been building the JIT, we've been implementing most of the bytecode instructions by just calling to a C++ helper for those functions or for those instructions. And in many cases, we can implement the instructions directly in machine code as long as a couple of assumptions hold. So stuff like if you're doing ++i, as long as I is known to be an integer, we can implement integer increment in assembly rather than calling out to a generic C++ helper that can increment any JavaScript value. So that's kind of what we're going to be doing today, is that we're going to be implementing fast paths in machine code for everything that this loop program wants to do, so that it never has to call out to C++ helpers for any of the stuff in the hot path. And actually we did get a whole profile here, so let's take a look. We can see if we scroll up to the top that CXX increment is our heaviest. Then we got CXX LessThan. So both of those two are essentially the workhorses of that loop, which makes perfect sense. If we look at the loop again, what we're doing is we're checking if it's less than this, then increment that. So increment and less than. And yeah, if we implement fast paths for those, for the case where I is known to be an int32, as we call it, then we never have to call out to C++. So let's do that. And I guess the first thing I should show you is that that's sort of how increment kind of works in the bytecode interpreter already, I guess. At least I think it is. Let's look at what less than does. Less than, yeah, so if we look at the generic less than, it does have an optimization where it checks if both sides are int32. Then we'll just do a direct compare of those int32s instead of going into the more generic code path. This optimization is not in the spec. The concept of an int32 value is not in the spec. It's just something that we implement in our engine sort of as an observation of a JavaScript value that we check, oh, this thing has no decimals and it's in the integer 32 range. Let's just say that it's an int32 and allow ourselves to do things like this. Anyway, point is to say that we have the metadata to tell us that something is an int32, and then we can use it as an int32. For increment execute, that actually does a toNumeric followed by, depending on if it's a number or a big int. Yeah. So here there isn't actually a fast path for int32, although maybe toNumeric has one. Yeah, if is number, which checks is int32. But I think incrementing a big int is far less common than incrementing an int32. And incrementing a double is also less common. So here it is. I'm a little bit surprised that we're doing double math here and we're not specializing for int32, but in the JIT compiler, we're definitely going to specialize for int32. So let's take a look at increment first, I guess. So increment right now, we can see how we compile it. we just compile it as a load from the accumulator and the VM into argument 1, and then we make a native call to cxx increment, which does exactly the same song and dance as the bytecode interpreter does, just a 2 numeric followed by a literal +1. So what we want to be doing here is checking if the accumulator is an int32, then we have to check if it's an int32, and actually we also have to check that it is that it's not going to overflow if we do +1, because the int32 range ends, right? And if you try to increment past the end of the int32 range, then it has to become a double. So for that reason, we need to call the C++ helper if incrementing as an int32 would overflow. So here, I would really like to have some kind of primitive for like, oh, if the value in this register is of this value type, then do something. So let's invent something for this. So like branch if int32, arg1, and then maybe we can have like a lambda that generates code for that case. Let's see how we would do that. So it would be like template type name cogen or something like that. And branch if int32, assembler reg, cogen. Okay. And then we can like, if it's an int32, we end up here and we can do the int32 case. I think that would be kind of nice. Hopefully kind of ergonomic. We'll see how it feels to actually use it once we have it. Okay, let's test it out. Or let's see how we would implement this. So first we want to, well, I guess we need to check the top bits. So the top 16 bits of reg, which the easiest way to check those, let's just copy them into a second register, operand register GPR0. Gonna copy the register there, and then, because then I have it intact, and then I will shift it. Shift right GPR0 by 48 steps exactly to get the top 16 bits into the bottom 16 bits, because then we can do an equality check. And it also conveniently gets rid of everything that isn't part of the value tag. So let's see. Let's write here what we're doing. So GPR0 is reg. GPR0, or actually we can even write it this way, 48. Now we want to check if it's an int32, or if it's if it's an int32. So we have to do a jump if equal, and we want to check the assembler operand register GPR0. We want to compare that with a constant, which is going to be the int32 tag. And if that is true, then int32 case. We could also have jump if not equal. We could say like not int32. I guess, I don't know which one is favorable. I'm sure there's some science and some information about this. I've definitely heard people say that you should try to make your happy path not branch. So like you should never, it's most efficient if you don't jump away from your happy path, which means that the happy path should be that's an int32, so we should only branch in the edge case. But I don't have any data to back up that thing, and this is also not the time to be worrying about this type of micro stuff. There will be a time for that later. So let's make a label for that. So not in 32 case. Let's call it, I like to call these case. So we make a label. Then we're going to, so now we are on the happy path. So here we do our cogen, which is the lambda that we're being passed. And then after that, I guess this is the not in 32 case. So we just link that to here. Okay, so this jump just jumps over the cogen, right? And then it's up to the cogen to do whatever. Yeah, so if the cogen wants to like jump to the end, for example, which would probably be a reasonable thing to do, then massembler jump end, which apparently is not a thing yet. Okay, I can't jump to a label. I really want to be able to jump to a label, so let's just add that. Or void jump label, which needs to, I guess, just jump to the target, rip relative, and yeah, right, we set the label slot offset to wherever we are right now in the instruction stream, although it should go after the jump. That's how our label thing works. Okay. Good. So I think here, now we have a fast path for, if we are in 32 that we're trying to increment, we now get here and then just jump to the end and don't increment. So if we run right now, I guess it would run forever. That's how I would expect it to work. Let's see, at least see that it does that. Yeah, it does seem to run forever. Or at least slow enough that I got tired of waiting. So now we need to add one to, we need to add one to arg1. And we need to do that in such a way that it doesn't overflow. There might be some like bit fiddling tricks here that we could do, or like we could use 32-bit registers and check the overflow flag, or I don't know. But let's just do it in the sort of brute force simple way, because it's still going to be a million times faster than calling C++. And then we can come up with cool tricks later. So what I want to do is just say like, we have to mask away the top bits. We only want the bottom bits now. So we want to do this essentially. Yeah. So in order to do that, we need to bitwise and we have to be careful here because although it's a 32-bit immediate, these are 32-bit immediates when used in a 64-bit context are sign extended. So this will actually just extend 1 bits all the way up through the whole register. So we need to use an im64 like that, essentially, if we want to mask the bottom bits. I'm sure there are easier, there are like smaller ways to do that. Like you can do other kinds of tricks, but we're not gonna do tricks. In the future, we'll do more tricks. And then we want to add one to it, I guess. Or we can also, actually, we can just check here if it is, like if it is, I guess if it is 7FFFFFF, that means that it would overflow if you add one to it. So if arg1, right, if it is this, then we want to go to the slow case, which is calling native helper. So, okay, so let's have a slow case label as well, and we link that up here. So like that. And of course, we're keeping the original accumulator value in arg1 the whole time, which just nicely lines up with the native call here to increment. And for that reason, we should probably actually move it out So GPR0 is arg1 and. Yeah, let's do that. So move it over first so that we don't disturb arg1. And then jump if equal. And I think in this case we can use an im32 because it will be sign extended, but the most significant bit, the sign bit, is 0 here, so it will sign extend with zeros all the way to the left. So that's the slow case, and then this should say GPR0. But now we're on the happy path, so here we can just add 1 to it. Not to arg1, GPR0. And we could let's see. Yeah, this makes sense. I was going to say like we can use an inc instruction maybe even, but we don't have to get fancy right now. So now we have incremented the int32 part. We have to put back the int32 tag in the top part of the value, or we have to add it back somehow. So let's see here. Let's also, we don't need the exception check if we're doing the fast path. Yeah, so we want to poke the result into the accumulator after adding the int32 tag, shift it up by 48. Okay, so I think for that, let's just load it into another register. Yeah, exactly. And we'll load it as a 64-bit. And is there like a, yeah, there's like a pre-shifted constant for that. Yeah, let's just use that. Okay, so GPR, yeah, bitwise OR, GPR0 with GPR1. Oh, we don't have with bitwise OR. Let's add it. Bitwise and. Can I get a hand, Copilot? Maybe not. Do I have to write it myself? Well, we can. Oh, no, there it came. And I missed it. Here we are. Right, so we got register, and we got register im32. Those should be okay for now. So let's see. Okay, so now we have the fully formed JS value in GPR0, and we just have to jam that into the VM accumulator register before leaving. So store VM register, accumulator, GPR0, jump to end. I think that's the whole fast path. Okay, not quite. We're crashing in assembler. Oh, shoot. Why are we crashing in assembler? Line 316. Right here, bitwise and. Okay, I tried to do something that I don't know how to do. Bitwise and. Oh, I'm bitwise anding with 64-bit value. That's not a thing. Oops. Right. So I guess I have to put that into a register before I do that. There's no, you can't, and none of the bitwise things work with 64-bit immediates. You have to mov the 64-bit immediate into a register first. Okay. So we put that into GPR1 and then, with GPR1. Sure. Hey, it definitely felt faster. So we're down from 1.14 to 0.6 seconds with this little fast path. That's pretty cool. It's a substantial speed up. Let's see, what about our Kraken benchmark? I'm just curious. You're running AI A star. Just get a hyperfine on that. .3. Yeah, how fast were we going before these changes though? Okay. Not bad. Not bad. So 300 milliseconds less per run of this Kraken subtest, just from adding a fast path to Increment. And let's just make sure the overflow case works correctly. So I guess we'll do something like ++I console.log I. I don't know how to read that offhand. Yes, it correctly became something that could represent this number instead of overflowing and staying as an int32, so it didn't become like -1, right? Let's see if we do that twice, it still works. Yes, it still works. Awesome. Okay, great. Git. Oh, wait, shoot. I was testing with the unchanged code. Oh, no. Okay, so we do have a bug. Okay. So just the one increment causes a bug. Can it show you here? Like, okay, that's goofy. All right, so it's not supposed to do this. So we're supposed to jump to the slow path if it's 7FFFFF. So how did we mess that up? Jump if equal to the slow case. Wait, I am linking the slow case to here. Let's see if we're calling that helper, CXX increment. Machine code to dev null. Yeah, we're not calling the helper. Why are we not calling the helper though? Let's just insert a break here. I really want to have like a debugger trap or something. Debugger. Let's call it trap, and then let's just add a thing for that because it's nice to have. Yeah, exactly. Just a int3 instruction just to trap in GDB so we can look at what the state of the registers are at that point. Okay, so args, run, yes, we've trapped. What is the state? So here, GPR1 and GPR0, we've ANDed, we think we've ANDed off the bottom bits. I don't think we have though. What is going on here? So this is GPR0, this is GPR1. Are they backwards? Oh, maybe bitwise and register to register is backwards. I guess that would explain it. If so, we'll just swap these. Let's let's see, source and dust. So source is 3 shifts. Yeah, so it's probably going to be the same for bitwise OR. I bet you that was the problem. Let's try that again. Okay, now GPR0 has only the bottom bits, so it's indeed 7FFFFF, as we would expect. So let's remove the trap and see that it prints out well, 7FFFFF. That's what I'm incrementing, right? But why am I not logging anything afterwards? Suspicious. Okay, so we're taking the slow path. Here, slow case, call increment. Put the ret register in the accumulator, check exception. Everything's good. Let's see if we do it twice. Does that work? Okay, so we do that. What is I at this point? Why doesn't it come out? Am I just doing something dumb? Oh, I'm sending it to dev null. Okay. I'm smart. Okay, yeah, it's good. It's good. We're good. Good shape. So let's see. I just want to fix up the AND instruction first in a separate commit. Okay, so git commit lib.js JIT fix encoding of x86 64 and dist source. Actually, that should have said reg. Okay, and then yeah, we can bring all these guys in. No, that's okay. We don't need to overthink it at this point. lib.js JIT add fast path for increment with in32 value. This uses a new branch if in32 mechanism that takes a code generating lambda whose code will run if the input register is an in32 JS value. Very cool. So that we fixed a couple of bugs that we found there thanks to this, but I think this is a very reasonable approach to a fast path, and it can definitely be more ergonomic than this, but I already like the branch if mechanism. I think we can get further with that. So if we were to profile now, what would we see? Let's just grab another one. I would expect CXX increment to be gone, and it would be all CXX less than, which would be then our next fast path target. So actually that makes me need to recheck Kraken also, because I was testing that with bugs. I mean, it's not necessarily the case that they have overflows in Kraken, but let's check it nonetheless. Yeah, it's still fast. Very good. Very, very good. Okay, so let's look at our profile with the increment optimization in place. Now it's all less than. And of course, here is our mystery JITted code. The call grind or cache grind, they don't know what that is. And you know, one day we're gonna have to figure out how to actually communicate to profilers what code was executing in that memory page. I don't know if there's a way to capture that, but I'm sure there's some mechanism that you can use to communicate to profilers. But right now, we gotta look at this guy, because we have 100,000,001 calls to LessThan. So yeah, we can probably fast path those as well, because we know that both sides are in 32. That's and this is a super common case in JavaScript, right? That you're just using something that fits in a 32-bit integer. You're using it to iterate. This pattern, not uncommon. So optimizing this, very, very useful for real-world code. So let's see, where is LessThan? Right, we don't have LessThan as a separate thing. It's part of the binary op stuff. Enumerate common binary ops. Right. So it's nice to have them in a macro like this, but it kind of screws me over when I want to put an optimization in a specific one. So let's see. What's the least disgusting thing I can do right now? I'm thinking like I can duplicate the macro and make one that has like not LessThan, because over time we're probably going to want to add fast paths to almost all of these, or probably all of them actually. So the use of the macro will probably disappear over time as we make JIT code generation for them. So I think maybe that is less disgusting than I initially felt. So without fast path, we'll do that, and then we say LessThan. You don't get to be in the list, because then we can use this everywhere. So enumerate common binary ops. Just paste that over. Cool. Because this allows us to add our very own compile LessThan. This is going to be cool. I would just have to make sure that we actually invoke it. So case, bytecode, instruction, type LessThan. Thank you, Copilot. Very nice. Binary ops. So binary ops follow a very simple pattern that we have as a macro here. So I think we can essentially just take this and use that as a starting point. So LessThan, remove all the macro gunk, and LessThan. All right, almost in shape. Okay, so this is the basic outline. Currently, LessThan will load a left-hand side operand from the instruction, and the accumulator is the implicit right-hand side, calls out to this helper, and then puts the return value in the accumulator, checks for exception, and we're good. And oh, I never mentioned it explicitly, but in the increment case, we don't have to check for exceptions if you're staying within in32 range and there's no overflow or anything. There's no way that will throw. So we can actually just skip the exception check in the fast path, which is nice because that's less things to do. So now, let's see. I guess we can load them up into these registers here, first of all. because it's kind of nice to just let them stay in those places, because that makes fall through to the slow path easy peasy. And then now let's do branch if in 32. Although I only want to go the fast path if both sides are in 32. So let's maybe invent a new mechanism called branch if both in 32. So something like this. And then what am I thinking? I want to make a slow case label here. So let's see, auto slow case, make label, and I also want an end label. And my end label goes here as usual. And my slow case goes here. Okay. And then let's see how we do branch if both. Should be pretty straightforward, just doing the same thing for 2 registers before invoking the cogen thingy. Branch if in 32. So this guy, can you guess what I want to do next? Not yet. We'll call that LHS and RHS, I guess. So let's see. We kind of have to follow the same pattern as the first one, where we just put them in a temporary, shift them right to look at the bottom bits, and we just have to do that twice. So that's essentially what Copilot is suggesting here. So GPR 0 is left-hand side shifted 48 times, and GPR 1 is right-hand side shifted 48 times. And let's see, not in 32 case. Make a label, jump if not equal. So we're checking both of them one at a time here. I guess this is pretty reasonable. Although this makes me realize that I have 2 jumps to the same label. That's not going to work because of how we implemented labels. So let's first do the fast path, but then we could look at making labels able to have multiple jumps to them. Yeah, so like fix me. Use one label, one assembler label supports multiple jumps to it. Okay, so what have we done? We shifted it 48 steps. Same thing with this guy. If they're both in 32, cogen. Otherwise, we end up here. Yeah, I think that's good. Branch if both in 32. So at this point, we have 2 in 32s, which means that we have 2 64-bit values, and they have the int32 tag, both of them in the top 16 bits. And then in the bottom 32 bits, we have a 32-bit integer value. And I think, does that mean that we can just compare them? We should be able to do that because they will look sort of like this, right? Like whatever the int 32 tag is. Yeah, 7FFA. So they will look like this, like 7FFA, however many, and then like 1, 2, 3, 4, 5, 6, 7, 8. Something like that is how they will look in hex. And not exactly, but something like that. And I think because of that, we can just do a straight up 64-bit less than instruction in assembly, or a compare and then jump if less than, I think, because we can ignore the tag. Yeah, because of the tag, the sign bit never changes. Yeah, let's see if we can do that. So like if arg1 is less than arg2, return true, else return false, essentially. So assembler, we need a jump if less than instruction, but we can invent that. arg2, that's the true case, I guess. So in the true case, and in keeping with what I was saying earlier, but like, let's try to keep the happy path branchless. Maybe we should have the false case be jumpy. You know what? Let's not think too much about this. Jump if less than true case. True case, link m assembler. But here is the false case. So it's not less than, which means that, yeah, we're gonna load a false JS value encoded into GPR0 and then put that into the accumulator. Like that. And in the true case, oh, here, let's jump to end. Yeah, m assembler jump end. In the true case, we load true and then store that into the accumulator and jump to the end. And again, we have two jumps to the same label, so let's just hack it for now, and we will come back to this. Unify when we have multi-jump labels, sure. Jump if less than to the true case. Okay, so now we just have to do jump if less than. We have jump if equal, jump if not equal, void jump if less than. You can probably infer everything I want to do. Thank you. Okay. I wonder if this is going to tell us that, because we've only been doing equality checks before, so I wonder if we will discover that the encoding of left and right for compare is wrong. We'll know that soon enough. Oh, I have to say operands here. True case, all right. That is too fast. 4 milliseconds. I don't believe it. We are probably having exactly that bug where compare is backwards. So yeah, I think we have to swap these. No? That was not the issue? Okay, something else is the issue. Although, let me just say bitwise and destination. Like destination and source versus LHS, RHS is a little bit confusing. But source is sort of the RHS in these cases. Let's not overthink that, but we will see what we're doing. So JL for jump if less than, that seems good, but it feels to me like we're doing something wrong here. So branch if both in 32. We should probably let's see, if we're in the fast path, let's just trap and see what the state is. Wrong file. Okay, so we have our inputs are arg1 and arg2. So those are SI and DX, just so that we know what we're looking at. SI is a int32 value with 0, and DX is some nonsense. Interesting. That does not look like what I expected us to see. Wonder if our program has encoded correctly. Should probably look at the assembly for this just to make sure that we're not totally goofed. So actually now we have an interesting problem because we're emitting assembly for 2 functions. So there's going to be there's more than one function in the assembly output. So let's do a little bit of a trick to see if we can get the global context to not compile. So let's just do something we haven't implemented. For x in object, yeah, we haven't implemented that, so it will fail. Which means we only get output from 1, which means that we can disassemble that. A very scientific approach. Okay. So where is our less than? Actually, you know what? Let's do a less than JS, and we just say 2 less than 3. We will compile that, and we will end-asm that. So this is only a less than. Empty program with just a less than, I think. Well, a little bit more. Load immediate, and then a less than. Sure. So where does our less than start? Here is our int32 trap. So that is, oh, that's before we branch shift both int32. Okay, anyways, how do we look at both int32? So let's see our code generation here. Sure, so arg1 goes into GPR0, we shift it right 48 times. Arg2 goes into GPR1, shift it right. Comparing them to the int32 tag. If it's not a match, we go to D6, which is our bailout point, I guess. That is not int32. So here, D6. And this is just where we exit. Or no, sorry. This is where we do the native call to CXX less than. So that's good. You can recognize the native calls easily because they push all of the caller saved registers. Okay. So we didn't jump to D6, which means that then we do a compare. Compare arg1 and arg2. And then less than. If less than, then we jump to C0, which is here, where we store true into RAX and then jam that into the bytecode accumulator register. Finally jumping to 190. 190, which is where we exit the JIT code. Okay, so what I would want to see is right before we do the compare, what's in the registers? Compare, jump if less than. So, I mean, the generated code looks good, but maybe I made a logic mistake. Wait, I put a trap there, but it doesn't trap. Okay. So how am I screwing this up? Branch of both. How am I screwing it up? let's trap here. So we should have 7 FFA in both GPR 0 and 1. Seven FFA, but here's a 0 in GPR 1. Okay, so GPR 1 is supposed to be RHS, which is arg2, which is RDX. So RDX has some nonsense when we're coming in here. That doesn't look like anything. And I'm loading the accumulator into it right here, which doesn't look good. arg2, RDX, yeah. Let's trap right after we load the accumulator into arg2. Okay, it's 0. That doesn't seem right. So how are we screwing this up? Let's see. If we change the loop so it doesn't increment in this way, I'm just going to check. What if I do like this? Segmentation fault. Oops. That's not good. Oh, because we have a trap there. Trap, 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 trap. How on earth are we screwing this up? We need to look at the code again. So we look at our LessThan implementation. No, we should look at the full program now. Let's look at loop.js. And then we want to look for the shift right, where we're doing it twice. Here. This is going to be our fast path. So we're checking, are you both in 32? Sure. So fast path is here. Compare, LessThan, 13D, otherwise here. And it seems to me like we're loading something bogus into the into R2 here. I wonder if we're here, something goes wrong with instruction encoding. Yeah, there's something a goof. So what are we doing here? This is mov into arg2, and this is definitely not the right. This is not the right register, or not the right source. And then we have an add that's not supposed to be there. We have a lock prefix on this guy that's not supposed to be there. So we've corrupted the stream. Usually when we corrupt the stream is because we are patching up a jump to a label that went bogus somehow. Did I mess that up? So the labels that are close to here are end1, end2, slow case. End1, end2, and slow case. Those are all linked to down here, but is anybody jumping to all of these, actually? and 1 is jump to here, and 2 is jump to here. Slow case. Oh, nobody's jumping to slow case. Okay. So that's probably what's causing it, because we create a label that gets an offset in the instruction stream, and then we link it here, but nobody actually calls it, so it doesn't actually have a jump slot. Right, because if both are in 32, there is no slow case. You always go to the end, because if both are in 32, we can always resolve the situation. Okay, we should fix that issue when we do multi-jump labels. So now we trap, sure. So get rid of the traps. And now it feels like it runs 0.836. Wait, are we here? Less than, let's see. Can't tell if we're here or not. Probably we're here. We should be going faster, I would imagine. No? Are we indexing? We're running clang tidy. Okay. Okay, it's finished. Let's try one more time. Oh. I know what's different. I did this thing here because I just wanted to perturb the code. Let's put the optimizable increment back. And look at it go. 0.3 seconds. Yeah, this is the speed. Let's do a couple of runs. Wow, look at him go. That's awesome. So cool. Right, so now we have fast paths for increment and less than, which is everything that this program does in the hot path, essentially. So this is sort of our, now we have implemented fast path for both. So we're at sort of at our architectural, this is not, what architecture allows at the moment in terms of like architectural optimization, but there's going to be definitely more micro and mini optimizations possible. I think we can emit better instruction sequences. We can get better at encoding instructions, like it's like using smaller immediates and things like that. And we can also get better at emitting less dead byte code, which would turn into less dead JIT code. But even so, getting it down from, where were we when we started? 1.14 seconds to 0.3 seconds. It's pretty nice. So where does that put us on Kraken at the moment, on AIA star? 4.2. I feel like, okay, maybe less than is not a huge huge factor in here. We have some loops like that, some loops here. Yeah, there are definitely some loops, but there's more to life than just less than in this one. So less impactful. But in our dumb loop here, it is it's all about that less than. So now if we val grind here, let's see what our profile ends up looking like. See, yeah, I think my intuition about compare was good, by the way. Okay. So now we are in this mystery thing here for 99.73% of runtime. This is essentially happy mode for this JIT architecture, which is that we stay in generated machine code the whole time. That's awesome. Never have to call out to C++ helpers. And look how much faster we can go. Great. This is pretty cool. So let's see. Let me just do the compare instruction fix first of all. The JS JIT fix encoding of comp reg. And then lib.js JIT add fast path for less than in 32 and 32. This uses a new branch if both in 32 helper. Note, it's interesting to note that we can compare encoded in 32 values with without stripping the in 32 tag, since it doesn't affect signedness of either values. Yeah. Cool. That is really cool. So let's see. Let's do multi-jump labels, since that's kind of frustrating. So the way that I put together labels originally was just like each label has an offset into the instruction stream where the jump slot for that label is. But I think we're going to do something like this instead. Offset of label in instruction stream. And then we will have a vector of offsets, jump slot offsets in instruction stream. And then maybe like add jump, something like that. That would be cool. And when we link it, we just iterate over offset instruction stream jump slot offsets, something like that. Yeah, that seems more like it. Link. Yeah, so we're linking from where we are right now when we do the link to where the I guess where the label is, right? So offset of label in instruction stream. Okay, so when we make a label, that's the offset of the label that we're setting here. And when we're jumping to an existing label, we just add a jump to it. Okay. Add jump. And then we can have many jumps. All right. And then we only need one, which is a bit nicer. And then you only have to link one label. Cool. Not in 32 case. Yeah. Okay, not quite. Shoot, how did I dumb this up now? Let's see, can we compile LT? We cannot. So am I doing some visible screw up of the instruction stream? Not seeing it immediately, but I'm sure I am. JZ. Make a label. The offset of the label in the instruction stream is where we are at the point where we make the label. Right, and when we link the label, we iterate over all the jump offsets, all the jump slot offsets, And then we're going to poke into that jump slot a relative address from the jump slot. Oh, wait, no, not from the jump slot. The offset needs to be relative to the jump slot. So was this correct? When you call link, it's because you want to link it to here. You don't, so you want to change the offset. It means you want to link it to here, right? So offset of label is mf of size. Okay, loop. Okay, I'm just dumbing this up now. So why is it failing? Let's look at our jumps. Don't have any crazy looking jumps. Oh, there's a jump with the dead beef still intact. After an and something with one. Bitwise and M1, and then we create a jump to end, which we link here. Okay, so what happens then? We make a label. Oh, here. We make a label, but we never add the current offset to it as a jump slot. That's how this thing is supposed to work. It creates a jump. So label, jump. Let's do that, and then that. Look at him go. Oh man, that's pretty cool. That is pretty cool. So yeah, that's much better. Let's see that we can still run the Kraken test. Still runs. Very nice. Yeah, performance hasn't changed. Good. Okay. libjs JIT allow multiple jumps to the same assembler label. Cool. Yeah, that's excellent. Okay, so I think we have achieved what I wanted to achieve today, which was to go fast in the dumb loop. And I'm really happy with the outcome. Definitely had a little bit of struggle on the way, but you know, when we're just exploring new territory like this, it takes time to figure out patterns and learn what the typical mistakes are so that you don't keep making them again and again. But I think in general, this was very interesting, and I think we can plow forward with more optimizations like this. We're definitely going to be finding better and more ergonomic ways to do these things. But even so, like this doesn't feel overly complex to me. Like this is pretty understandable. The control flow is pretty good in the JIT, I think. It can probably be better, and we'll find ways to make it better, but in general, this feels like a step in the right direction. So cool. All right. this will be the end of today's video. So if you made it here, thank you for watching, for hanging out. I hope that you saw something interesting, and I certainly enjoyed making this thing go as fast as we can do with these fast paths, at least. I don't know yet what we're going to do in the next video, but it will be something that moves us forward somehow, incrementally, which is what it's all about. So thanks for hanging out today, and I will see you all next time. Bye.